Hello everyone, welcome to another example of discrete random variables, specifically the hypergeometric random variable. So your challenge in the course is going to be identifying the different types of random variables. Once you have that, you have equations to work out the calculations for probabilities, expected values, and variances. So how do we recognize hypergeometric? Well, first, it has some components that are not too different from the binomial. So the binomial, you've got a checklist, a criteria that allows you to identify whether or not it in fact is a binomial random variable. The hypergeometric, to identify, has selection without replacement, and by default, all selection examples in probability classes are without replacement. So if a problem were to intend for you to replace, it would specifically state it. Otherwise, I would just assume that the selection is without replacement. The other component that you need is you need to know the contents of the pool of objects. So contents known. And in essence, you're counting, like the binomial, number of, quote, successes. And again, the success is just the item or object that you are interested in knowing how many of them you ended up with. So in this example, we have a classroom of 13 students. We are going to select 3 randomly. And then the question's asking about the components of the group. So in this particular question here, of the 3 students that we are selecting, what's the probability that there are no freshmen in the group? So if I stay consistent with the notation in your course, then the hypergeometric has these parameters that you want to be able to go through. So the uppercase N is the total number of objects, in this case, students we have in our pool. So we've got 13. The lowercase n is always going to be the sample size, or the number you're selecting. In this case, it's 3. And the uppercase S will represent your total number of successes in your pool of objects. So again, the success is identifying what you're counting. So we're interested in the number of freshmen in the group. So that means my total number of successes will be freshmen, in this case, 8. And then the little x that you see in the PMF equation, the little x is going to be the desired outcome. So if we want no freshmen in this case, then our desired outcome, right, is x equals 0. So from here, I've got an equation. Let's write out the equation. Again, we've got a PMF equation. It's just a counting rule. That looks as follows. Now, this is a little sophisticated, so let's break it down. So we know that for any probability, you're just going to count the number of ways that you could obtain the event of interest divided by the total number of ways that the experiment could happen. So if we're interested in, well, what's the chance we don't get any? Then our experiment here is we're choosing 3 students out of 13. So we have in total 13 choose 3 ways that we could perform that operation. That would give us all the combinations of selecting 3 students out of this class. But for hypergeometrics, we have this binomial situation where it's a yes or a no. In this example, it's either freshman or not. So that means I'm just going to take the classroom and split them into my 2 groups. So I've got freshmen and then non-freshmen. So freshman group is 8, and then the rest of them, combining sophomores and juniors together, is 5. So since the question is only asking about freshmen, then that is my success. Everything else would be considered not a success. And then what you're picking and choosing from here is just what the question's asking. So if we want no freshmen in the group, and again, let's highlight it here, then out of this group of 8 freshmen, I'm going to choose 0. And since my experiment is that I have to select 3, that means all of the other students will be from this group here. Right? So you can map this into the equation in orange on the left if you like, or you can just logically break down your total classroom of 13 into yeses and nos, in this case, freshmen and non-freshmen, and then you're just going to highlight. And once you're here, you've got a calculator where you can punch in all this combinatorics, the choose function on the calculator. And if my math is correct here, this should be 035. All right, so let's take another look at a different scenario. In this follow-up, same experiment, but now my interest will be, well, what's the chance there are 2 sophomores in the group? So what's changed for us is our definition of the success. So in this example, I'm interested in counting sophomores. So that means I still have a total of 4 sophomores. So now my capital S becomes a 4. And what I want is exactly 2 of them. So here the little x will now be 2. But the setup will be exactly the same. I want the probability that I get 2 successes. Since I haven't changed the scenario, I have the same classroom, the same experiment, picking 3 students, then my denominator is still 13 total, choosing 3. But in the particular setup, I've got 4 sophomores now total, and that means I have 9 other students that aren't sophomores. And again, I don't really care about the particular breakdown. I'm just looking at my contents of my classroom into sophomores and non-sophomores. And then again, the question will dictate, well, how many of each do we want? We want exactly 2. So in this case, 2. I'm still picking 3 total, so that means I have to have 1 student. And again, I don't particularly care if the student's a freshman or if the student's a junior. All right, I just want to make sure that my group has exactly 2 sophomores. And that's basically it. This is how we plug it into our formula. And again, plugging it into my calculator over here, I'm looking at almost 20 or almost 19% here. And that is it.